Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be talking about the actual meaning of our quantum field. So in our previous videos, we talked a lot about operators, the creation operator, the annihilation operator, how to solve these equations. We haven't yet talked about the actual role of the field in quantum field theory. So let's talk about that. So what is the meaning of our field phi? In today's video, we'll be dealing with a free scalar field, but in our future videos, we'll be moving on to spinor fields and vector fields and interacting fields. So let's begin. So first of all, we have our postulate of quantum field theory. These are the commutators of the annihilation operator and the creation operator. So basically, what we want to actually find out is what is the product or the inner product between our actual momentum eigenstates. Because remember, these vectors are eigenstates of the momentum operator. So a useful thing to know is the inner product of these eigenstates. Now we know from quantum mechanics that it should be something like delta of k minus k prime, meaning that this product represents the amplitude that we find a particle having momentum k. So if you were to graph this, we would get a delta function that peaks at where k equals k prime, so like maybe right over here, and it's zero everywhere else. So we should find a similar result in quantum field theory, and indeed we do. So how would we actually evaluate this product? What we have to do here is recall that our momentum eigenstate is just a result of us acting on our vacuum state with the creation operator. This implies that the covector 1k prime is going to be the conjugate of a conjugate k acting on the vacuum state, and that's just going to be a of k times the covector vacuum state. Because recall that a conjugate k is just a of k conjugated, right? And if you conjugate that again, we just get back an unconjugated expression, that being a of k. So by using this knowledge, we can expand this out. We can expand 1k prime times 1k out as the vacuum state times a of k, and then a conjugate k. Well, this should be a k prime, by the way. So then a conjugate k acting on the vacuum state. Cool. What we have to do now is use our commutation relations here. In this case, let's let this guy be the k prime, and let's let this be the k. So using our commutation relations, we know that a of k prime times a conjugate k minus a conjugate k times a k prime equals 2 pi cubed delta of k minus k prime. K is a 3 momentum, by the way. This implies that this expression right over here, a of k prime a conjugate k, is going to be equal to 2 pi cubed times our delta function plus a conjugate k a of k prime. So all we're doing is just solving for what's inside of here. So we can just plug this expression right over here inside of this one right over here. And that's going to give us vacuum state times, and then we can just distribute our vacuum state on the inside, and that's just going to give us delta of 2 pi cubed delta k minus k prime acting on our vacuum state. And this term is going to go to 0 once acted upon by our vacuum state, because a of k prime times delta times the vacuum state is just 0, right? So once we distribute this onto this part, we're just going to get 0. And now, since this is kind of like a constant, we can just bring it out to the front. And that's going to give us 2 pi cubed delta of k minus k prime times the vacuum states multiplied together, and they are defined to be normalized. So you have 1. So we are just left with 2 pi cubed delta of k minus k prime. And that is our answer. So this answer makes sense from the context of quantum mechanics, since we know that in quantum mechanics, when we take the inner product of our momentum eigenstates, we get a delta function. Here we have it scaled by 2 pi cubed, but that doesn't really matter at all, since for k is not equal to k prime, we get 0. And then for k equals k prime, we get infinity. So it doesn't really matter that it's scaled by some constant over here. Now, of course, this momentum eigenstate is kind of like an unphysical state in the sense that we can't have an initial state that's a momentum eigenstate. Our initial state has to be some sort of superposition of those momentum eigenstates. So, yeah, that's pretty much how we take the inner product of those states. Now what we want to find out, right, is the actual meaning of our field phi. How do you find the meaning? Our field contains the creation and the annihilation operator, right? It contains those factors. So since those are operators, that implies that the field itself is also an operator. So if the field is an operator, then what do we get when our field acts on the vacuum state? Like, what's our answer? You know that when we act A conjugate K on the vacuum state, we get one particle with momentum K. So maybe, just maybe, when we act on our vacuum state with our field itself, we might get some sort of eigenstate, maybe a position eigenstate. Maybe it's one particle with some position x. Could that be the case? Well, to actually find what that is, you have to actually carry out this computation. So let's do that right now. So I've written out our free scalar field right over here. So what we want to find out is the field acting on the vacuum state. So all we have to do is, it's pretty straightforward. We have to multiply both sides by the vacuum state, and then we have to distribute this vacuum state on the inside. If we distribute it, we get this over here. And now we know that A of k acting on the vacuum state gives us 0, right? So that means that this term gives us 0 when this goes to A of k. And A conjugate k acting on the vacuum state gives us one particle with momentum k. So when this goes over here, we're going to get this over here. This implies that phi of x mu acting on the vacuum state is... So here's our answer for our field acting on the vacuum state. You can see that it actually gives us some new state, but how do we interpret this state? Well, recall that an integral is just a continuous sum. So really, we're just adding a bunch of momentum eigenstates that are scaled by some plane wave. So we're just adding a bunch of continuous plane waves, and by adding up a bunch of them, we get some sort of new state. Now remember from quantum mechanics that if we take a continuous sum of plane waves, we actually get a function localized at some position x. We get a delta function for a position. So is that the same case here? Well, to actually find that out, we have to take the inner product of this new state with itself. So from quantum mechanics, again, we had that x prime times x is delta of x minus x prime. That just means that the amplitude for finding a particle at some position x is going to be like infinite for that position and 0 for different locations. So let's first assume that this is actually a position eigenstate. Let's call it 1x, where x is going to be the 4 position, right? So if our assumption is true, that means that 1x prime in a product with 1x should give us delta of x minus x prime. Or again, this x is going to be the 4 position in space-time. So how do we actually calculate that? Well, it's pretty much the exact same steps that we did for the momentum eigenstate. That's right over here. So all we have to do is just note that 1x prime is just going to be 1x conjugated, right? And we know that 1x is just the integral. So the conjugate of that expression, conjugating this and changing x to x prime, gives us this over here. We change e to the I k mu x mu to e to the minus I because when we complex conjugate an expression, we have to change the sign if it's a complex number there. So what we have to do now is simply multiply ix prime with ix. And that's going to be a pretty messy multiplication, so we're going to speed up the video. So we have this over here. So let's just erase what's on the top to make this a bit less of a strain on our eyes. So we have that this is equal to this. Now we can simplify this long expression over here. We know that this is just going to be 2 pi cubed times our delta function, right? And this 2 pi cubed will cancel out with this one right over here. And we know that when we have an integral over a delta function, it's a good thing because it makes the integral pretty easy. Recall that the integral over some delta function of x, and we have, or should be delta of x minus a times f of x is just going to give us out f of a. This implies that our integral over here, like this one right over here, because we're integrating this first and then again with respect to k. So the integral of just what's in the yellow underline is going to be e to the I k mu x mu e to the minus I k mu x mu prime. And then times of 1 over the square root of 2 omega k. And then again, we changed k prime, like we let k prime equal k, because this delta function implies that our integral is 0 for when k prime is not equal to k. So we set k equals k prime. We did not set x equals x prime because our delta function was not over position. It was only over k, not x. So we still have that x mu prime over here. And then again, we still have to integrate again, but over our variable k. And again, we have a factor of 2 pi there. Let's bring this integral down a bit. Here we go. So yeah, we have this over here. What's convenient for us is that we have a square root of 2 omega k times square root of 2 omega k. That's just going to give us 2 omega k, right? So we have 2 omega k. Sorry for the previous interruption. Those are my sisters. They can't get enough of me, you know? So we have this over here now. Pretty sweet. So we can rewrite this out as e to the minus I k mu times x mu prime minus x mu, right? Because this is going to give us e to the minus I k mu x mu. That's over here. This gives us e to the I k mu x mu. That's right over here. And then we're integrating over that. So we are integrating over that. We're integrating over k. So now we have this right over here. 2 omega k. Cool. So what's the answer to this integral? it looks very much like the integral for a delta function-ish, right? Because remember that the integral, remember that delta of x, right, is just the integral over dk over 2 pi cubed e to the minus I kx. This integral gives us the delta function, right? Because again, it's just Fourier analysis. It's the Fourier transform of a plane wave is an localized spike, right? And that's kind of like what's over here, except for this pesky little 2 omega k. It's almost like the format for a delta function. We have 2 omega k. And it would be great if omega k was a constant, because it wouldn't even matter at all, right? But since omega depends on k, and we're integrating over k, we can't just move it to the front, right? Because omega k is, again, it's our energy, it's square root of k squared plus m squared, where k is the 3 momentum. So the actual answer to this integral won't actually be a delta function. In fact, for large distances, so when x prime mu minus x mu is much larger than 1, and let's just redefine this to be r, the distance between the 2 points. For large distances, this expression behaves like the function e to the minus mr, where m is just some scalar constant. And if we were to graph this for positive distances, you would get something that looks like this. So it decays for large distances, but it approaches infinity for small distances. Now, this isn't a delta function, because a delta function should have a peak at r equals 0, which is just x prime equals x mu. So our delta function is what's in the yellow. That's delta of x, or I should really write delta of x mu. And what's in the pink is what our expression is actually equal to. So it approaches that delta function for small distances, right? But for large distances, we still have a non-zero amplitude. Whereas for the delta function, we have precisely 0 amplitude. So this tells us over here that this expression over here isn't actually a delta function. Or in other words, the inner product of 1x prime with 1x isn't a delta function, which means that the result of our field acting on our vacuum state does not give us a true position eigenstate. It only gives us an approximate position eigenstate. If you were to solve this integral, like precisely, there isn't an analytic solution. The actual solution to this integral, let me just copy and paste it for some organization. The actual answer to this integral is going to be m over 4 pi squared r k1 of mr, where this k thing over here, it's called the Bessel function. We've actually encountered the Bessel function in our videos on the hydrogen atom. Yeah, so, and the Bessel function can't be written in terms of elementary functions. So if you know what a Bessel function is, this might be illuminating. If you don't know what it is, well then, it doesn't really give much. But that's the actual solution to the integral, and it's not a delta function. That's what really matters here. So, yeah. So since even though it's not a delta function, it does still kind of act like one, because remember from quantum mechanics, we know that the momentum eigenstate times the position eigenstate, that was a plane wave, right? I think it was e to the minus I kx. Or ikx, I can't remember which one it is. I think it's e to the minus ikx. So so what happens when we have ix acting on, or sorry, 1x acting on 1k, where 1x is going to be our field acting on the vacuum state, which again is not a delta function, or sorry, it's not a true positional eigenvalence state. We're still gonna write it as 1x because like it's just for convenience, but it's not truly an eigenvalence state. But what happens when we kind of do this in quantum field theory? Like, what's the analog here? It's actually pretty easy because we already found out what 1x is going to be. We found out that it was this expression right over here. Right over here. This over here was equal to 1x. So 1k prime, which I should be writing k prime, acting on 1x, that's just going to be the integral over k, 2 pi cubed, square root of 2 omega k, and then 1k prime. That's why I use k prime, so we can use the delta function here. Acting on 1k, e to the I k mu x mu. And that's just going to give us a delta function, 2 pi cubed, delta of k minus k prime. Again, because that's what we found out earlier on in the video. We found out that it was that. So scrolling on down, these 2 pi cubes cancel out. And then again, we can just let k equal k prime. So that's just going to give us our answer as being x mu. So yeah, this should be a positive ikx. Cool. So yeah, that's our answer to what's the inner product between ik. I keep calling it I don't know why I'm calling one I. I don't know why, but when I say ik, I mean 1k. And then 1x. Or 1k prime, but it doesn't really matter. Because k equals k prime. We just use k primes when we want when we want to exploit the delta function. So this is kind of like a plane wave, but again, we have this factor over here. Because in quantum mechanics, we had k in the product with x. That was just going to be e to the ikx. In quantum field theory, we still have this pesky term over here, right? So again, it just tells us again that this 1x is not a true position eigenstate. It doesn't represent a true delta function amplitude vector thingamajig, right? But it's kind of approximately one, right? You still have that plane wave there. It's just scaled by a factor of 1 over the square root of 2 omega k. So, yeah. And that's pretty much it for this video. Oh, also, if we were to graph this out, again, we're going to have something that looks like a plane wave, which makes sense. This is telling us that the momentum eigenstate, in physical space, or I shouldn't say physical space, but if you were to kind of graph what it looks like, it looks like a very spread out wave. It's very delocalized. And this is a consequence of the Heisenberg uncertainty principle, right? It tells us that if we have a more preciser function, or if we have a much more precise position function, we're going to have an imprecise momentum function. So since 1x corresponds to a sharp peak, right, or approximately a sharp peak, then 1k is going to correspond to an elongated plane wave when we graph it. So those are how the amplitudes kind of manifest when we graph them. So yeah, that's pretty much concludes this video. And an important thing to note is that this over here, where is it? This over here, what's in the pink or now the yellow, it's called the elementary propagator. The elementary propagator. And the elementary propagator tells us the probability amplitude that we have one particle that's around some position x propagates to some new position x prime. Again, it's not a precise position eigenstate, but it's approximately one. And we call this expression, this inner product, we call that the elementary propagator. And we are going to be dealing with propagators a lot in this QFT series, because propagators tell us, these propagators, in general, they tell us the amplitude that a particle propagates some distance. And the elementary propagator tells us the probability amplitude, the P amplitude, that some particle propagates from x to x prime. And we find out that that's going to be 0 if x does not equal to x prime, or approximately 0, because again, it's going to decay but not strictly be 0. So we are going to encounter some new propagators in the future. We will encounter the retarded propagator. We will encounter the dynamical propagator. I'm not going to bother spelling it. And then the most important propagator that we'll encounter shortly is what's called the Feynman propagator. And the Feynman propagator is what's used a lot. It's used in scattering. Virtual particles, if you've heard of those are actually just propagators. So we'll be dealing with these three propagators shortly in the next couple of QFT videos. And after that, we will switch on to spinners. So yeah, thanks for watching this video. I hope you guys enjoyed it and have a great day. Bye.